Once again, we're going to consider this bimolecular reaction that we can write in sort of an abstract way as A plus B goes to products. But in this instance, rather than looking at fundamental collision theory, we want to consider it in more thermodynamic terms. And so we want to look at, in a sense, the mechanism or the steps by which a reaction might undergo this change. So what we're going to do is break this into a sequence of partial steps. So this bimolecular reaction could be an elementary step itself, but we want to break it down even further. And what I mean by that is when these two molecules come together and have a collision, we're going to suppose that somehow they come into equilibrium, although this isn't a real equilibrium, but they come into an equilibrium with an entity that is sort of along the way to getting to products. All right, so let me draw what I mean here. So let's suppose that this is our general reaction diagram. This is a reaction coordinate or reaction progress. And this would just be an energy axis. So the standard picture looks something like this, where we go from reactants on the left, so that's A plus B, to products on the right, and we won't even specify what those are. And as this goes through, it goes over this area we call a transition state, which is, of course, the focus of this particular theory. And what we're supposing is that at the top of this barrier, there is an activated complex, okay, which we're going to call X. And I'm going to put a little double, whatever you call it, this symbol on it to indicate that this is at the transition state. Now, if you want, you can think of it as being kind of a flattening of the barrier so that there is something that sits there long enough for us to characterize it. But in truth, there isn't. This is not a true equilibrium. This is a construct for the purposes of modeling this process. But we're going to assume that these things form some sort of equilibrium, and then this activated complex can go to products. But the whole idea is that the collision of A and B might form this activated complex, and then it could go right back to A and B. That's why we have this reverse arrow here on the bottom forming that. Now, if this were a real equilibrium, we could form an equilibrium constant that might be something like this, where we have the concentration of this activated complex divided by the concentrations of A and B. And in fact, we're going to use this to our advantage as we formulate what happens here. Even though this activated complex is not, it's a transient species, it's not something that is going to last for very long. Now, the whole idea behind transition state theory is that we want to relate the transition from reactants to products as a frequency for crossing this transition state. So I'm going to define this Greek letter nu, which looks a lot like my italics V, but it's a Greek nu, and we're going to say that this basically is equal to the frequency for crossing the transition state. And that being the case, we can, in a sense, define the rate now for this reaction as being equal to this frequency for transiting the transition state times the concentration of things that are at the transition state. So this frequency is really relevant to this activated complex, this thing, and I should probably make a special designation here. X is the activated complex. All right, so this frequency that we're talking about is really relevant to that activated complex, and we're going to define it in such a way that it really comes from that definition. But I want to note that if we can write an expression like this down for a supposed equilibrium constant, we can also use this to write down an expression for this concentration of the activated complex. So in other words, I can write this as nu times the quasi-equilibrium constant times these concentrations of the two reactants A and B. Now, the reason for writing it this way is that this looks an awful lot like our fundamental differential rate law for a bimolecular reaction. So by writing it this way, it allows us to make an identification of these constants here with the rate constant. So in other words, I can write that the rate constant is going to be represented by the frequency for crossing the barrier times this, I keep calling it a quasi-equilibrium constant, but there's not really a good term to use for that. All right, now how would we define these things? So we still need to find some kind of expression to quantify these two things. All right, now what I'm going to do is I'm going to associate this frequency nu with a vibration in the activated complex that actually leads to the transition of the barrier. So in other words, nu is going to be somehow related to a vibration in the activated complex that facilitates crossing. Okay, so there's one coordinate, say, that does that, and we're inherently assuming that it's a vibration, but that is probably a reasonable assumption. Now, how would we get a handle on this value of nu? Well, it turns out that what we really care about is the activation of nu, that is to say, the energy that has available to it at a particular temperature T. Now, remember that when we were talking about partition functions and we were talking about vibrations, that we associated the energy of vibration with its frequency by h bar times omega, where omega was an angular frequency, if you will, for that oscillator. But this is also can be written like this in terms of a frequency nu that's simply in units of inverse seconds. Where instead of having the reduced Planck's constant, we have regular Planck's constant. And so this is the thing that under thermal conditions we're going to associate with the Boltzmann constant times temperature. Now we were using this to determine, what was the probability of the vibration being activated into its V equals 1 state. But we can think of it very similarly here as the thermal activation of this particular coordinate that leads to the crossing of the barrier. But now this gives us a way to express the frequency of crossing, nu, and we're just simply going to write it as kBt over Planck's constant. Now, I apologize if my explanation doesn't make the connection for you. There's actually a lot more involved in doing this, but I hope that you'll accept that this is a way of representing this frequency, and in fact we're going to employ it now in defining our rate constant. Now the other thing that we need to do is somehow define this quasi-equilibrium constant. Now it relates to a process that starts in one state and ends in another state. So it's really not too different from the sorts of equilibrium constants that we were talking about in module 6. All right, which means that we can actually relate it, if you will, to a free energy or Gibbs energy change for making that transition to that activated complex. So I want you to think of this delta G0 of the activated complex is basically the Gibbs energy change for going from reactants to the activated complex up here under standard conditions, because that's what the 0 up here means, is under standard conditions. Now, when we have this, you'll recall that we could relate this to an equilibrium constant like this. And our assumption is going to be that these same relations will hold in this circumstance, even though this might be relating to a state or a condition of the system that is a transient condition. But it also means that we can relate these things to the enthalpy and the entropy changes for going from, so these are basically changes that are relevant to this particular reaction. Okay, A and B going to this activated complex. All right, so I'm going to continue using this double dagger, if you will, to represent these things so that we're always clear that we're talking about this process and not the overall reaction process. Now when we write all this down, it means that we now have a way of expressing this K double dagger, and I can now begin to rewrite my rate constant for this chemical reaction as now nu, which is given by this expression over here. So we'll have KBT over H, and then the expression for this equilibrium constant is e to the minus delta G0 double dagger over RT. All right, so all I've done is put in what we have found for these two quantities and substituted them into this equation. But I want to go a step farther, and I want to write out delta G as we've done up above here, so that I can write this rate constant as equal to this frequency factor times e to the, I'm going to put delta H and delta S in reverse order, so it's plus delta S0 double dagger over R, okay, because we're dividing by temperature here, e to the minus delta H0 dagger over RT. Okay, now the reason for doing this is to give you something suggestive to look at. And the suggestive thing that I want you to think of is that this here is a lot like our frequency factor, A of t. And this here is reminiscent of the e to the minus e sub a RT that over RT that we had from the Arrhenius equation. So in other words, these are the quantities that we saw in the Arrhenius equation, but now described in terms of thermodynamic quantities. All right. Now, we could also relate this. Remember, we wrote down for the collision theory result that, in fact, this frequency factor, A, could be written, sorry about that, could be written in terms of the P collision times this frequency of collision factor. And this in turn was P collision sigma AB times the average relative velocity, and I'll just write that this way. All right, so we have basically three models: the Arrhenius model, which is the simplest, the collision model, which is a little bit more involved, and what I'll call the thermodynamic or transition state model, which gives us a real connection to thermodynamic quantities up here, all describing this rate constant and its temperature dependence. And there's enough point of contact here that we can begin to draw some associations. So for example, this frequency factor, A of t, is related to the frequency of collisions, but we can also see that is related thermodynamically to the change in entropy when we go from the reactants to the activated complex. And in particular, if that results in a lot more microstates, that's going to greatly increase this frequency factor. That's going to cause this reaction to go faster. Now we find in most cases that this delta S is not very large, but there are some cases in which it is, and in that case we have a real enhancement of the reaction rate due to that factor. Now it's tempting here at the very end to make an association between delta H and the activation energy. And while I'd love to tell you that, yeah, absolutely, let's just associate that, it turns out it's a little bit more involved than that. Now, I could go into some detail about this, and it actually is not very difficult to follow, but I'll simply say that E of A is actually better related to, I should make this delta U, the internal energy of that activated complex, but it's delta U plus RT. And when we go through the thermodynamics to relate delta U to delta H and consider the molecularity of the problem, it turns out that this is really equal to delta H plus MRT, where M is the molecularity of the reaction. So for this bimolecular reaction, M would be equal to 2. All right, so EA is indeed related to delta H, but it's not exactly equal to delta H, and that's something I think it's useful to file away in the back of your mind. Now, I want to say one last thing, and that is that a couple of videos ago we had made an association between the empirical equation that related log of the rate constant So it looks something like this. Log of the rate constant was, and is the derivative of this with respect to temperature, was related to the activation energy over RT squared. And I said that this was kind of reminiscent of the Gibbs-Helmholtz equation, and that we could, in using that, we could sort of relate log of K with minus G over T. Well, in fact, that's exactly what we've done right here. In fact, that is a relationship. And I said that we would then also relate the activation energy to the enthalpy change. Well, that's exactly what we've done here, relating the activation energy to an enthalpy change. The difference here, though, is that the enthalpy change is not the enthalpy change of the reaction. It's the enthalpy change for going from the reactants to the transition state, and that's an important difference. So I hope this has made sense, and that you have some appreciation now for the beauty of transition state theory and the connection between thermodynamics and chemical kinetics.